Hello, awesome mindsetters. Welcome to This is your grade 10 physical science show. You know what? I'm super excited for this show because I'm not alone. I'm with John. Mr. John, how are you?
I'm really well, thank you. Good afternoon, grade 10s. Great to have you with us. And it's first day back for term 4. Hey?
Yes.
Can you believe it?
There's not much time now, John. It's just the last term, unfortunately.
Yeah, that's right. And you know what? There's not too much content as far as physical sciences is concerned. But I know that we've got some exciting news coming up. And
Very
you're going to
exciting.
talk about exam revision.
Let me talk about exam revision, helping the mindsetters. As Mindset, we have partnered with Samsung to bring you the Samsung Learning Hub application with so much revision that you can get for yourself. Let me take them through on how it looks like.
Absolutely. You go for it.
Right. Mindsetters, as you can see, I'm not bragging. This is how awesome this application is on a Samsung tablet. You must be using a Samsung tablet or your premium smartphone to be able to access the hub. Now, it looks like this. You have a video and also a question paper, which is so interactive. Actually, what you can do is to answer the questions on it. That's the first thing that you can do. And you're able to see the video at the same time and see your question paper. But otherwise, in viewing your question paper, you can fill in the answers, right? And then after filling your answers, then that's when you can check out the answers that are there at the end. You see? You've got your solutions right there. So, which is great that after watching the video, you interact also with the question paper, answer your questions, and then you can check out your solutions. But this is just like the last part on how I got here. I just want to take you through on the beginning. I wasn't bragging. I just wanted to show you how cool is this. So let me take you through the Learning Hub. On the Learning Hub, it looks like this. You have shelves with your books that you have already purchased on the hub. Otherwise, if you need to look through and find out other material that you do not that you'd like to buy or that you'd like to view, you need to go to stores. Right there, there's a trolley there, and then what you'll see, there's a voucher that you're gonna see this screen, and then you need to go to brands. On brands, you look for Mindset Learn. And when you click on Mindset Learn, you'll be able to see all the content that Mindset has. We have so much content and it's being uploaded almost every day. We're bringing so much stuff, physical science, life science, maths, all the subjects that we are doing on Mindset. And they're so cheap. You know, you can get products from 8 Rand 37 and there's so much to them. Now let's just see if I like this video. I can click on it just to view what is really happening. It is electrochemistry. I can see that there are some checklists, there are some questions, and there's some solutions, and also there's some videos that I can check through. And then as you can see, this one, it's already purchased, meaning if it's purchased, it's already on my library. I can check it at any time. But if you have a video that is not purchased, you're going to be getting such a message like this one, or a screen that says you need to buy that or add it to your basket. If I want to buy it, I'll click on buy. Then there's a screen that's going to pop out for you. Here, voila, a free 100 Rand voucher, proudly brought to you by Samsung. Then I can use the voucher or use my own credit card to pay. But now because my total on my basket, I only have one item, which cost 8 Rand 37. I can't really pay because I need to save my money. You only get one chance whereby you need to use the whole 100 Rand. Otherwise, if I just use this 80 Rand, I'll be losing the rest of the money that is on the voucher. So I'm not going to buy Mindsetters. Instead, I'm just going to take you back to the shelf so that you see that after having purchased your product, what do you have? So when you get here, you go to your library, and then there you go. You have the material on your bookshelf, and then you can click on it. You don't need to be connected to the internet for you to view it. And the nice cool thing about it is that you can check the marks also about it. So this is what Samsung is bringing to you, Mindsetters, and I think it's a very cool innovation. Stay tuned to find out more because Samsung and Mindset are bringing you so much cool stuff. John?
Really cool stuff. Thanks, Abram. But you know what? I think we need to get into today's lesson as
Yes,
well.
and let me just give them the tools though.
Absolutely, go for it.
Before John tells us what are we doing today, all you need to do to be in touch with us, go to Facebook. Our page is facebook.com/Learn Extra. Like the page, chat on the page, ask some questions, and also get other mindsetters to help you on the page. But otherwise, you can still download the notes all for free on learnextra.co.za/live. But for now, enough talking, because I'll be giving you more information also about the help desk that we have on Mixit. So stay tuned. John, what are we doing?
Abram, thank you so much. Guys, Abram mentioned something really important. Doesn't matter what device you've got, if you want to get today's notes, where are you going to go? You're going to go to learnextra.co.za/live and have a look here. I've just opened it up. And what I'm noticing is that a lot of people are saying on the help desk and sending us emails saying, where do we get the notes? Well, here's the platform. You'll see the particular page that I've got open here has a blue box. And that blue box, I'm just writing around it there, has got the word notes on it. Click on the word notes and download the notes and you'll be able to follow us. Now, what are we doing today? We're going to go and talk about energy. Let's have a look at our objectives. Our description for today, we're going to, first of all, we're going to do the following things. We're going to define and calculate gravitational potential energy of different objects. Then we're going to define and calculate the kinetic energy of objects. We're also going to state and apply the law of conservation of mechanical energy. Now that's quite a mouthful, but we'll get to that in a little while. Let's get started by just doing a brief overview. Some of you have done this sort of stuff about energy in grade 8 and 9, so let's just do some quick recap and revision. So when we talk about energy, it's a word that we use every day. Like we might say to Abram when he's falling asleep behind his desk there, we might say to him, Abram, what's the matter? Your energy level's down. Now, guys, don't let him go to sleep. Put some questions on the board there. Keep him busy. Keep him answering. Post your questions. Anything that you want to know about energy, tag it on the page. Chat to him on Twitter and make sure that he stays awake there. So, energy. When we're talking about energy, we also think about food. And some of you might be recognizing that food has different amounts of energy. You might be watching how many kilojoules you're consuming, or how many calories you're burning when you go to the gym, or all that sort of stuff. Now, the important thing for us to recognize, even though we use this word energy, it has a very clear scientific understanding and meaning. And there are really only two types of energy that we will deal with in normal situations. And that is potential energy and something called kinetic energy. Now, both these forms of energy, potential energy is kind of stored energy. We're going to look at a particular type of potential energy, namely gravitational potential energy. And the second type of energy is kinetic. When we talk about kinetic, and there are a whole lot of words that are related to that, it means energy of motion. Both those energies are measured in the same SI unit. The SI unit for energy is something called a joule. Now, I mentioned calorie earlier. It is another unit of energy, but it's not an SI unit. When we're working with energy, we only work with joules. Of course, you can get a lot of joules, and then we say kilojoule. But when we're doing calculations, make sure we work in SI units, so we must convert from kilojoules to joules. So what do we know about gravitational potential energy? Well, it's stored energy. It's energy that an object has due to its position in a gravitational field. So in the notes, what we've defined it and said, gravitational is the energy that an object possesses. It belongs to an object as a result of its position in a gravitational field. So here we are standing on the earth at the moment, and I'm not actually on the ground. I'm standing 1 floor or 2 floors above the ground. So in relation to the ground level, I have some gravitational potential energy. because if suddenly the floor went down below me, I would fall back to the ground. So I've got stored energy because I'm at a position above the ground. And the gravitational field will pull me down back to the zero position. The zero position is usually indicated as ground level. But we could have said, let the zero position be the roof of the building that I'm standing in. So we can define the reference point. And I hope you understand that. We will have a look at that a little later. So, next thing, how are we going to calculate gravitational potential energy? We use this equation, EP, E standing for energy, P for potential. Even though it's gravitational potential, we're saying EP, and we're using the symbol M, G, and H. G is the acceleration due to gravity. Now, it depends on which planet you're standing. Now, unless they say what the planet is or the object is in the question, we will assume it's on Earth. And I want to remind you that the acceleration due to gravity on Earth is 9,8 meters per second downwards. Because gravity is always going to act downwards. Remember, acceleration is a vector. We've dealt with acceleration at the end of the last term, and here we've got an acceleration again. What about the m? Well, the m stands for the mass of the object, and it's measured in kilograms. And the h is the height above the reference point, above the ground, and it's measured in meters. Now, when we multiply these together, what you need to understand is that we produce a scalar quantity. So remember, vectors have direction. Scalars don't have direction. So here, potential energy, gravitational potential energy, is not a vector. It is a scalar quantity. So we'd recognize that it's a scalar quantity. Abram, how are we doing on the page? Any questions so far?
Yes, here's one from Benny Tawang saying, is energy vector or scalar?
Okay, I've just answered it. Okay, so energy is a scalar. Just remember that. Now, I don't want to get into too many difficult calculations about that, but just be aware, it doesn't matter how I get to the height above the ground. I could say, I want to get the energy of this pen that I'm using, the stylus that I'm using to write on the smartboard. It doesn't matter if I lift it from down here in a roundabout way and eventually gets to that position. It still has a certain amount of potential energy. Whether I lift it straight up or I lift it in any way, it will still have the same amount of potential energy because we're measuring the height above the reference point. In this case, we'd measure the height above the ground. Okay, so let's move on because I want to do the last bit of definition here, kinetic energy. Kinetic comes from a Greek word that's the same origin as the word cinema. Cine, meaning movement. Okay, so what is a kinetic? It's the energy due to an object's movement. Very important. We're going to define it according to this equation. The object has kinetic energy, Ek, which is equal to half m, which is the mass, and the v here is the velocity squared, but we could also take speed here, and we're not too fussy whether it's the speed, instantaneous speed at that moment, or it's the velocity. We don't really need the direction in this calculation. We'll just assume it is in a particular direction. We square it. Don't forget the squaring in when we're doing the working out. That's very important. Okay, so now that we've defined those things, let's have a look at a couple of questions. And let's see if we can get through them. I'm just going to introduce this first question to you. And let's see how we go. And perhaps give you some time to look and see if you can do it. So here we go. How much gravitational potential energy, so we know we're looking for EP, we know the equation that we're going to use is EP is equal to the mass times the acceleration due to gravity times the height. And remember, what we've said is that if it doesn't say what planet it is, we're going to take it to as being on the Earth. So is transferred to a metal ball of mass 40 kilograms. So we know the mass is 40 kilograms. Okay? If it is lifted to a vertical height, very important that that height that we're looking at is vertical. It's straight up and down. It is actually a kind of a vector. It's the position vertical above the ground. So a vertical height of 30 meters. So 30 meters. And it's above the ground. And we're going to assume that this is on Earth. And we're going to say that's 9,8 meters per second, like that. Now, we don't have to substitute in direction here. What we're saying is this object has been lifted from the 0 position and it's gained kinetic energy. Not gained kinetic energy, it's gained potential energy. It's got stored energy because it's now resting up at 30 meters above the ground. Have a look at a quick diagram. You know that I like to draw little sketches when I'm doing this sort of problem. I'm going to say, there's the ground level. We're going to take that as 0 potential energy. And that's 0 joules. And we're wanting to know what this energy is at 30 meters above the ground. There's the little steel ball, and we're going to put it like that. And we know that it has a mass of 40 kilograms. Sorry, 40 kilograms. How are we going to do it? I think you've got it. Really easy. Substitute in, and let's see if you can get the answer. Abram?
I've
In the
posted
break,
the question
let's see what
also.
we get the answers.
Yes, let's find out, Manchesters, if you can do this. But otherwise, stay tuned. Tell all your friends that we are learning more and learning extra right here on Learn Extra 319. See you after this. Welcome back, awesome mindsetters. Now, you might be saying that I'm just a grade 10 learner, but now in mindset, there's no one who just stays like that. We are upgrading you guys, promoting you rather to the next slot. Now, from the 14th of October, still doing your revision, we are having an exam school whereby your time slot now will be from 5 o'clock up until 6 o'clock. Isn't that great, John?
Absolutely. And guys, you know what? In that exam revision, we can't leave it too late to revise. So we're going to go back to term 1 stuff that could come in your final exam. We'll go over all that. So if you've got questions, please make sure you post them so we can answer those directly from the 14th.
That's so great. But now looking at the page, we have a couple of questions and your answers. Hopefully they'll be right.
Okay, let's go. Let's go.
Right. Should I give you a question?
Go for it.
Right. Here's Sarah Albert saying, what do they mean if they are saying potential energy is stored energy?
Okay, let's think about this. When we say something has potential, okay, it hasn't realized its outcome yet. So if we say, Abram, you've got the potential to be an engineer, okay? Is Abram an engineer yet? No, but he's working towards being an engineer. The output isn't engineering yet, okay? So if you've got the potential to be something, then you're not there yet. So in the same sort of way, objects have potential energy. They're not releasing their energy. Their energy is inside them, okay? In this case, it's energy due to its position in the gravitational field. So when we say we've got gravitational potential energy, it has the potential to be acted on by the gravitational field, which will cause it to move. So if we take an object, and I'm just going to take one off the desk here, this little tape, and I say, above the ground, this has potential. It's not moving at the moment. It's being held in the gravitational field, but it has potential to move. If I let go, it starts moving. And the force of gravity, or the force of the gravitational field, acts on that object and causes it to speed up as it falls downwards. That changes its potential energy, which was stored energy, into kinetic energy. So there's a change of energy from stored energy and it's released as energy of motion. In a similar way, I suppose we could say that we don't just have gravitational potential, but we have chemical potential energy. So think about it this way. Don't go and fill up tonight at your favorite filling station, because the price of fuel will be coming down tomorrow. But when you put in some of that chemical stuff that we call petrol or diesel, it's got stored energy in it. When we burn it, it releases an explosive way that is able to push your cylinders, which turn the wheels, which give you motion. Okay, so it's stored up. It's like held inside, just waiting to go. And when we release it, it produces motion. Okay, hope you've got that. Abram, makes sense?
Yes, it does.
Okay, another question. Any?
There's no question, it's just answers.
Okay, let's check if my calculator works. We're taking the Casio calculator for a spin this afternoon. So we're going to do mass of 40 times mg 9.8 times the height, remember, was 30 meters. And there we go. And we get 11,760 joules. So I'm going to just write that in over here, and I'm going to say, without too much further ado, we're going to say the mass was 40, the acceleration due to gravity was 9.8, the height was 30, and we got 11,000, what was it?
760.
760, and there we go, 760 joules. Guys, make sure that you get the right units. Don't just leave it as 11,760. Of course, if they said change it to kilojoules, we'd have to divide by 1,000. So what we have to say, 11,76 kilojoules. Okay. Excellent. Let's move on. We're going to question 2.
Can I just quickly ask, ask this based on that? I'm seeing that a lot of mindsets, instead of 9.8, they said 10.
No. Guys, please bear this in mind. We must remember 10 is a kind of rough estimate. Please don't use 10 as the value for G. It must be 9.8. You will get penalized in your final exam if you don't use 9.8. Of course, if they tell you that you can use 10 in the question, then you can do that. But mostly, we will take 9.8 as the standard acceleration due to gravity. When anything falls on Earth here, it's the most accurate value that we will use at school, 9.8. Okay, so please don't use 10, use 9.8. Right, here we go to the next one. Of course, here's an interesting one, because now we're not on the Earth, we're on the moon. And it tells us the acceleration due to gravity is 1.6 meters per second per second. Now remember, that's downwards. Just because we're on the moon doesn't mean things fly off. It's still, the action of gravity is downwards. It says, calculate the mass of a stone that has a gravitational potential energy of 40 joules when placed 50 centimeters above the surface of the moon. So we can't get this too wrong. Let's write out our equation. We're going to say EP equals mg, and we're going to put there moon, just to remind us that we're not on Earth, times h. We've been given that the mass is what we want to find. We've been told that the potential energy is 40 joules. We have been told that the acceleration due to gravity is 1.6 meters per second to the -2, and we're told the height above the moon's surface is exactly 50 centimeters. Now guys, can I use the 50? Can I use the 50? Think about it carefully. Absolutely not. Never, ever, ever use 50 centimeters. What must you do? You must use SI units. The SI unit for distance, for height, is meters. So we've got to divide by 100, which means that's going to be 0.5 meters. Let's now substitute. Now, don't get fancy here, guys. Lots of people will say, oh, I know how to do this. I'll just change the subject to the formula. If you get it wrong, you lose all your marks. So don't gamble. This isn't the lottery. This is time for you to get marks. So I'm going to substitute my values in. I'm going to say 40, and it's 40 joules. I don't have to put the units in. I'm going to say I want to find the mass. The acceleration due to gravity is 1,6. The height was 0,5. So now I can change the subject of the formula. I can say, therefore, the mass is equal to 40 divided by 1,6 times 0,5. Well, I know that's 0,8. Half of 1,6, 0,8. And I can then do the division. I'm not going to trust my head to do it, even though I could. I'm going to do it on the calculator. So I'm going to say, just to check myself, 40 divided by 0,8 equals 50. And I'll therefore write down the answer of 50 kilograms. Please be careful that you use SI units. Don't think that this is suddenly now on the moon it's gone to grams. No, 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 no. We are dealing with meters, joules, meters per second, and so we will get kilograms as our SI unit. Okay. Hope you've got that. Make sure that you substitute in. That's what I was going to mention to you. Guys, if you make a mistake on your calculation here, okay, so you get that wrong, you do something careless in your head, all you'll miss is that mark. You will get the mark for the correct formula. You'll get the marks for substitution. And that's 3 out of 4 marks that are going to be yours. Of course, if you don't get the right unit here, you don't put the right unit, you will lose this mark. You won't get it. Okay, so make sure, even though you get the right number, you will lose the mark because the unit is not correct. Okay, let's move on. We're going to question number 3 now. Question number 3 says to us, we're moving from potential energy, gravitational potential energy. We'll come back to it in a minute, but we're going to now go to kinetic energy. Have a look at what it says here. Calculate the kinetic energy of a golf ball of mass 45 grams if it's moving at 40 meters per second. Remember that the equation is EK is equal to half mv squared. Guys, don't forget that square. You must square it. Check yourself. Double check your answer. Okay, so what do we know? We know that the mass is 45 grams. Is that SI unit 45 grams? No, not at all. We must change to kilograms. It's one of those few that the units for mass aren't the standard unit. It's not like meters. It's not kilometer. Okay? But in mass, it's kilogram is the standard SI unit. So how do we get from grams to kilograms? We divide by 1,000. Another way of doing that is simply say we multiply by 10 to the minus 3. And that will be kilograms because there are 1,000 grams in every kilogram. So we've divided by 10 to the minus 3, multiplied by 10 to the minus 3, divide by 1,000, and that I'm going to leave like that. There's my mass. What about my velocity? That's what I want to find. What about my energy? I want to find, sorry, I wasn't wanting to find the velocity. I'm being given the velocity. The velocity was given at 40 meters per second. So 40 meters per second. And so I'm going to substitute in. I'm going to say half times 40 times this 45 times 10 to the minus 3. And I must square that. Don't forget to square it. So let's go to the calculator. And I'm just going to move the calculator over here so we get it right. And there we go. I'm going to start with the 45 just because I sometimes forget to square. And I don't want to make a mistake. I want to say it's minus 3. 45 times 10 to the minus 3, because I've converted to kilograms. I'm going to square that. So I'm going to say, make that a square, and then I'm going to multiply that by 40, and I'm going to multiply that by a half, which is 0.5. Put in the answer, and I get an answer of 0.0405. So it might look a little small, but we're still going to write it down. 0.0405 joules. Okay? Because this is a golf ball. Okay? We need to make sure that we've got it moving correctly. Guys, I've made a mistake. I hope you can see something. I've made a big mistake. Let me do it again. Because what I did is I squared the 45. I don't want to do that. I want to square the 40. So that's why I'm just thinking it was a little bit small. So let me just undo that and make sure that we get it right this time. Oh dear, that was terrible. But good thing I caught myself. Otherwise, I'm sure some of you would have seen it. 45 times 10 to the minus 3. And here, it's 40 meters per second squared. Kind of looked a little too small for my liking. 40 squared times 4.5 exponent minus 3 multiplied by 0.5, and that's much better. 36 is my answer, and I'm much happier with that. I did not like that previous answer. So what do we learn? Guys, always check yourself. Always say, is that realistic? Something moving so quickly, will it really have so little energy? Of course, if you get a very big number, check it, check it, check it again. So here the trick was to make sure you squared, but also to make sure that you did the conversion to the unit. So there were two little tricks. I hope you saw those tricks and that you're ready to sort them out. Abram, we're ready to go to a break.
Yes, I am. And I'm happy that the mindsetters are participating and answering also.
Excellent. Thank you, guys. Remember, if you've got questions, you can post them, and Abram's going to tell you where to.
Exactly. If you have some questions, post them on the page, or otherwise download your app. Get Mindset on your Mixit right now. It's on general context, edit, and get sharing. Submit your questions because we are willing to help you every day. Otherwise, we'll check you out after this break. Welcome back, Mindsetters. Now, earlier on the show, I told you more about the Samsung Learning Hub, but now I want you to keep your eyes peeled on the page because there's a great competition that is coming on our Learn Xtra revision called a marathon competition. It sounds fascinating and interesting, and I hear there are a lot of prizes to be won. Cool prizes sponsored by Samsung. So be on the look for that, Mindsetters. It's so great, and it's coming to you.
And
John?
you know what, Abram? If you download the notes, there's something in the notes tonight for you to look at. Okay, there's just something there. So get onto that page and make sure you get the notes. Grade 11s, if you've just walked in, get the notes from the Learn Xtra page. Download the notes. Make sure you engage with the questions. Try the questions yourself.
Exactly. And all the Mindsetters that are using Samsung tablets or Samsung premium smartphones, let us know, how's the Learning Hub treating you? Have you downloaded anything and have you redeemed your free 100 Rand voucher? Let us know. I'd like to hear from you on the page.
Shall we get going?
Let's get some. We have a question.
We got some questions. Let's go for it.
Here's a question from Libya Lisohonono. A stone is lying next to a deep hole in the ground. Does the stone possess gravitational potential energy?
Okay, that's an excellent question. So what you need to recognize is that when we defined potential energy, we defined it in the following way. We said that it is energy in relation to a fixed point. Now, whether that point is the top of a building, okay, or whether it's the basement, or whether there's a deep hole. Now, it depends on your reference point. Generally, at grade 10 level, what we will say is that the lowest point has 0 joules. But if I wanted to, I could make this point have 0 joules. So then what we would recognize is that anything that was below that point, so something that was below that point, so like you said, even there, that stone lying in a deep hole, it would have a negative potential energy. Okay? Now, that might seem strange because we've said potential energy is not a vector. But what it's meaning is that I've got to use energy to get it back to the 0 point. I've got to use up some energy. Some outside energy has got to be used to raise it to the 0 position. And the difference between what I have and what I would need to use to make it change its position to the 0 point would be negative energy. So this would be known as negative energy. Again, it's not likely that you would get this in a grade 10 question. But you can get negative energy, you can get positive energy. We usually like to talk about positive energy. And so for that reason, we would normally not say, no, guys, let's not define that as my 0 position. Let's not define that as my 0 position. Let's make this my 0 position. And then anything from there upwards is going to be a positive, a gain in potential energy. If I'm lifting it up, I'm gaining potential energy. So above the floor, this thing, as it's rising, this pen, as I'm lifting it higher and higher, is gaining potential energy. As I drop it, it's losing potential energy. Hope you've got that. Okay?
I hope they've got that too.
Any other questions?
No question, except that some mindsetters are writing their test tomorrow, so this comes in very handy.
Okay.
Make sure that you pay extra attention.
Excellent. So let's move on to the next concept, and I'm going to dash through this one very quickly. Often we're asked about mechanical energy. So what is mechanical energy? And it's very simple. Mechanical energy is just the sum, that means you add them together, of kinetic energy and potential energy. And we write it as mechanical E, mech E, or E mech is equal to EP plus EK. And the most important law probably in the universe, okay, and it's really important, is this one. The law of conservation of mechanical energy. And the law of conservation of energy is applied in many spheres of science, chemistry and physics. For us to understand this one, we're specifically talking about mechanical energy because we don't want to talk about situations where there is an energy loss, which can happen in a restricted sense. But what we're going to recognize that in most cases, energy cannot be created or destroyed. Now that's not totally true because we know that when we have nuclear explosions, there's a conversion of mass to energy. But for our purposes, we're going to say that in everyday life, energy cannot be created or destroyed. We're not going to think about what's happening on the sun. We're not going to think about what's happening in Coburg. But normally, we would say energy can't be created or destroyed. So, if I've got 10 units of energy at the start of an object, or of a scenario, I must have 10 units of energy at the end. Whether that energy is still kinetic, or whether it's changed into potential, it must still be there. Okay, what we're going to say is this is true only in something called a closed system. That the amount of mechanical energy is constant in a closed system. This means that there are no outside forces. So we're not going to allow additional forces like friction to use up the energy. Friction takes away energy. We don't want to deal with friction at this point. So there's just a little brief recap of the conservation of energy. Remember, conservation means things stay the same. They don't go up and down. The totals before and after are exactly the same. Conservation of mass means you've got the same amount of mass at the start of a chemical reaction as you've got at the end of a chemical reaction. Conservation of energy within a system, within an isolated, a closed system that's not having external forces that are going to use up energy or take away energy. The energy before and the energy after has to be the same. Right, let's see if we can apply this. So here we've got a little bit of a longer question, and I hope we can get this one through and finish it off. So let's read it first of all. It tells us that a boy drops a stone of mass 4 kilograms from a 45-meter high tower. Calculate the potential energy of the stone when it is still in the boy's hand. So guys, I'm going to start it one at a time, but I want to read the next one. It says, what is the kinetic energy of the stone just before it touches the ground? And then it says, using energy principles, calculate the velocity of the stone. Guys, this is a very common type of question, and I want to get through it and make sure that you understand each of these parts. So the first part is really straightforward. We've done an example similar to this in our earlier section. We want to find the potential energy. We're going to say EP equals mgh. We know that it's on Earth because it doesn't say it's on the moon, and we're going to say take down the value. It's a 4 kilogram mass, and it's in SI units. We know that the height is 45 meters, and we know that G is 9,8 meters per second to the minus 2. So having written that down, I'm not even going to worry with drawing a diagram. I'm just going to say it's 4 times 9,8 times the height, which was 45. Now, I hope you can see that that is quite easy. All you're going to do is plug it into your calculator. 4 times 9,8 times 45 equals 1764. So 1764, and the units are joules. So this was the potential energy of the stone before the boy let it go. It was stored energy. It was waiting to be released. As he let it go, that energy is converted because the stone starts falling. Notice that once it's fallen a little bit, it still has some potential energy, but it hasn't got as much potential energy as it had before. So when it's fallen a meter, it's lost some energy because it's no longer that high off the ground, but that energy is being converted into kinetic energy. And so it goes until it just above touching the ground. When it's just above touching the ground, all the potential energy is being converted into kinetic energy. So what are we going to say for part B? What is the kinetic energy of the stone just before it touches the ground? Well, we're going to say the following. We're going to say, and show our working. Now, guys, this is very important. You need to say the mechanical energy at the top is equal to the mechanical energy at the bottom. You can't just say, well, the kinetic energy equals the potential energy. Wrong, 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 wrong. You've got to say, we're citing the law of conservation of mechanical energy. And so what does this mean? It means that before the stone was released, there was EP at the start plus EK at the start. This was at the top of the tower. And this one is EP plus EK at the bottom. And they're both at the bottom, but I'm just not writing them in because I'm losing some space. So now what are we going to say? We're going to say the EP at the top. We've just calculated it. Now, guys, I could write mgh, or I should do, and this one is half mv squared is equal to mgh plus half mv squared. The setting out of this type of question is critically important. So please take note of this. Don't take shortcuts. You must substitute in. And even though I've done that calculation, I'm still going to substitute in my masses, which was 4 kilograms. And I'm going to say 9,8. And I'm going to say the height, remember, was 45 plus half. Now, before it left the boy's hand, was it moving? No, it wasn't moving. So it's 0 squared is equal to the mass, which was 4 kilograms, 9,8, And the height above the ground? No, well, it was 0. We still substitute the zeros in. Plus half m, which was, sorry, let's not put the m there. Half times the mass of the object, which I need to get, which was 4 kilograms, times velocity squared. Now, I don't know the velocity squared. This part here will help me in my next calculation. So what do I know? This turns out to be 0. This part here turns out to be 0. That part turns out to be 0. This part, we calculated it in the first step. It was 1740. Or no, 1764. 1764. And this is the EK of the stone just before it hits the ground. So can you see that what we can say by applying the principle of conservation of energy here, of conservation of mechanical energy, that the EK is equal to 1764 joules. Now, this, as I said, sets us up very nicely for part C. And I want to get through that to make sure that you've got it. Remember what it says? It says use energy principles. That means that you must use the equation that we've been talking about, the one I've just illustrated, the conservation of mechanical energy. Okay, you've got to use it. Now, some of you are saying, but hold on, we know equations of motion. We could do it by equation. Yes, you can. If it didn't say use energy principles, you're going to use energy principles and say that energy is conserved, mechanical energy is conserved, and so therefore we can find the velocity. We're going to say EK is equal to half mv squared, and this is part C, and we're going to say this one was 1764, this one was half, this one was the mass of 4 kilograms, that's v squared. So what I'm going to do, I'm going to use my calculator, and I'm going to say, let's take 1764 and let's divide it. Notice I've substituted first. I'm going to divide it by a half, which is 0.5, multiplied by 4. Now, I could have done that all by myself in my head, but I didn't. That's 882, just to show you that I've now got v squared is 882. Is that my answer? No, by no means. I've got to take the square root. So I've got to take that answer, and I've got to say square root of my answer, in brackets, is equal to 29,698. So I'm going to round that up to 29,70 meters per second. So there we go. We're going to say, therefore, V is 29,70 meters per second. And it's just second to the -1. It's per second. So let's make sure that there's no mistakes there. There we go. Guys, I hope you've got the plot, that you can see that we can apply we can apply these rules of energy. Now, challenge for you. Go and use equations of motion to confirm that the answer is actually right. And you'll see it is. Abram, are there any quick questions?
Yes,
because I know that we've got only a few minutes, but I'd really like to look at question number 5. But if we haven't got time, that's fine. I'll just start it.
All right, here's a quick one. Benson says, can you use the formula of potential energy to calculate the work done?
Okay. Now, guys, when we're talking about energy and work relation, this is something that you will study in much more detail in grade 12. But what we do recognize in grade 10 is we're just really working at potential energy and mechanical energy and kinetic energy. We're not really worried about this thing called work, but it is related. So if there's a potential energy gain, that is equal to the work done against gravity. If there's a potential energy loss, it's the work done by gravity. So bear that in mind. Okay. We okay with that?
Yes,
okay.
Cool.
Let's have a look at our last question for today, because I don't think we're even going to get this one finished, but we'll try and do as much as we can. So what it says is a boy of 50 kilograms has a velocity of 5 meters per second, and he's swinging vertically from a tall tree. He grabs it upwards. Calculate the maximum height that the boy will reach above the ground. Then asks a very interesting question that says, what effect will the increase in mass have on the height above the ground? And it says verify, do a calculation to verify. Now guys, I'm almost out of time. All that I need to say to you is what you're going to do is you're going to say mechanical energy before is equal to mechanical energy after. And if you substitute in the different positions, you will be able to work out the height that the boy reaches above the ground.
Thank you so much, John. Unfortunately, because of time, we have to end it there, Mindsetters. But the help desk is always there for you to submit your questions. Get it also on Mixit. It's accessible and it's easy to use. From us, we just want to say keep chatting on the page, and we love hearing from you. Peace out.